Hello, welcome to video 38 in the lecture Advanced Mathematic Modeling. So in the last lecture I started the discussion of equalities and Pareto rule, where we look when we have a power law distribution. How can we divide the power law into halves or in a certain fraction? And then on the one side we look how much, this would be a wealth distribution of people, and X is a typical wealth, then an area under this curve is a certain fraction of number of people, or a fraction of people, since it's normalized. And then we looked at fractions of people, but then we also looked at fraction of wealth. Yeah? And so you have, and these things you have to distinguish in mind. So like the fraction of people, so we integrate areas under the curve. But the wealth that is accumulated by these people is an integral of x times p of x, because that's the wealth in a certain fraction of people. And then if you do the math, then you see that the wealth in the fraction of richest people depends on the number of these people to power law again. And then we came to this curve here. Maybe I make this so larger so you can see this better. So then we obtain this Lorentz curve, and this tells us how unequal is this distribution. So when you first time see this, sometimes it's confusing for some people, or with all these fractions of fractions and so on. So you have to think a little bit through this. But so I gave you here many different examples, and sometimes if you, for example, now look at wealth of people, it doesn't really click for you. What is 80% and what does it mean? But then you think about phone calls, and then you remember, yeah, most phone calls I get from the same guys here. It's always my 3 best friends, they give me all phone calls. And then you can think like, so okay, what does this 20 then mean? So, so that's the 20% of the people who give you the most phone calls. And this is then the number of phone calls. So suddenly, for some people, it clicks if you think on the right example where you're most familiar with. Yeah? And so now I want to discuss this a bit further. And I cannot stress enough that this is not a precise thing. It's just it became so famous because, like, for a typical exponent that we see, the curve goes through this 80%, 20% point. And that's why it's called very often the 80-20 rule. But now if you take now a bit larger exponent, then this Lorentz curve looks a bit different. For example, this is how the Lorentz curve looks if we have something like alpha about 3. Yeah? And now the perfect equal curve would be a Lorentz curve which goes like this. That would be an equal distribution, because then the wealth would be totally equally distributed among people. Everybody has the same amount. And then if you increase the number of fraction of people, then you would get also linearly with the number of people more wealth. So actually this here, so this is our benchmark. This is a fully equal distribution. So if you have in the Lorentz curve here, the diagonal, that's a perfect equal distribution. So in some sense, or in some communist sense, this would be the perfect world. Everybody has exactly the same. And if we have deviations from the Lorentz curve, and the deviations then typically go, they always go up from the from this blue line. So the larger our Lorentz curve deviates from the blue line, the more unequal our distribution it is, and the more money or wealth is distributed among the rich guys. And so what happens if alpha is 2 or larger than 2? For smaller than 2, for alpha smaller than 2, we cannot even calculate this anymore. So the Lorentz curve in some sense doesn't exist, doesn't make sense. And for alpha equal 2 in the borderline, the curve goes directly here to 1 and then goes like this. So that's the other extreme, that's the curve for alpha equal 2. Yeah. So the Lorentz curve is then directly hits 1 and then stays 1. So basically mean an arbitrary fraction of the people has already all the money. Yeah? Now with these things, an arbitrary fraction of people has all the money. I mean, this can never be in a finite system, but this then just expresses the fact that we don't have in real world a real power law, so there will always be the maximal wealth that people have, and the power law will not be perfect. But if we would have a perfect power law, and then already for alpha equal 2, the Lorentz curve would be like this. Okay, and now the question is, now we can now try to quantify how far does the Lorentz curve deviate from the diagonal, and so we can have then a measure of inequality. So how can we obtain this? Yeah. And so let's look again at such a Lorentz curve. Here we have P larger of x, here you have the wealth, and the whole curve is in the square between 0 and 1. And then here we would have the diagonal, that would be the perfect equal distribution, and then we have a real distribution which deviates from this. And now Gini came with the idea to measure the deviation of the real curve from the diagonal. So that and to do this, to measure this, we look at the area. So this A is the area here in this part here. So the area of the Lorentz curve over the diagonal, and then the rest here, this area we call B. And then Gini said, okay, we have the Gini-coefficient, it's now called after him. G equals, so the fraction of A divided by A plus B. So the fraction of the blue curve divided by the whole fraction that's possible. Now, of course, since the Lorentz curve is here in the square between 0 and 1, A plus B is just half of the area of the square. So A plus B is 1 over 2. So you can express this also just as that's equal as 2A. Or you can also write it as 1 minus 2B. Yeah? So like if you have just one area, A or B measured, then you directly can calculate the other area because the whole triangle here has area 1 over 2. Yeah? But like this, it's more easy to remember. The Gini-coefficient is again a fraction, so it's a fraction of areas of fractions if you want, because the x's are also fractions. So it's a fraction of the deviation of the Lorentz curve from the diagonal to the maximal possible deviation. Yeah? So this means this Gini is a measure which is between 0 and 1. And so that's how the Gini curve is defined. The Gini coefficient is defined. And this is now our measure of inequality. Yeah? So if G equals 0, we have equal distribution, perfect equal, and G equals 1, that would be perfect total in unequal in equal distribution, because for G equal 1, I mean the Lorentz curve directly hits here the 1. This means an arbitrary fraction of people has all the money, and G equals 0 means we have the perfect world, everybody has the same share. And now we can calculate this. For example, if we have we have a power law with alpha larger than 0, then we can calculate the Gini coefficient as 1 over 2 alpha minus 3. Here, if you just it's just a simple calculation, you can do this. If alpha is larger than 2. And in Gini is directly 1 if alpha is smaller than 2. So for alpha equal 2, I mean actually for alpha smaller than 2, Gini isn't even defined. So actually Gini equals 1 for alpha equal 2. And if we, for example, take now so typical example of alpha equals 2.1, then we find a Gini coefficient of 0.833. So 0.8, that's already in equal world here. And now, so why can we use this Gini coefficient? I mean, like if you have a power law, the Gini coefficient is also related to the exponent. So why do we measure the Gini and not the exponent? Because the Gini coefficient then is more easy to interpret. It tells us something about the distribution. And now we can look for real world economics. Yeah. Yeah, and then so the wealth distribution is approximately power law distributed. But not perfectly. It's not a perfect power law. But you see, like the Lorentz curve, of course, in order to construct the Lorentz curve, we don't need a power law. I mean, you can construct when you have the data, if you have the amount of wealth of every person, you can calculate the distributions, you can calculate the cumulative distributions and the wealth of every person, and then you can calculate the Lorentz curve, even if you don't have a power law. Yeah. So maybe the wealth distribution in a country is not a perfect power law, it's just approximately a power law, but still we can calculate here the Lorentz curve and we can calculate the Gini coefficient. Okay? And now when we do this, then we can make a plot. And then we can take now time scale, time frame. Maybe we go here from 1950, maybe to year 2020. Yeah, so that's the time, the year we're interested in, and then we plot here percent of our Gini. And so on the top range, so Gini goes until, let's see here. Okay, I've prepared this a bit. So typical Gini coefficients, the range, so in about 20% to 70%. And now we can take a country like Germany, which has a Gini about 30%. And so actually for Germany, like according to some data, I mean, it depends really what kind of, how do you measure the income of people, and what exactly is the wealth you measure. Is this the people have in the bank account, the money the people earn every month from their work or whatever? So it's always, it depends a bit. But Germany has some Gini coefficient. It was a bit larger in some time. I think now it's a bit smaller, something like about 30%. That would be Germany. And now you take other countries in the world. For example, let's take for example England. England was here, so UK. UK was in the range, it was below Germany a long time, fluctuates, and then suddenly starts to increase. Yeah? So here you have UK, and then that's sometimes sometimes alarming if the Gini coefficient of a country is increasing, because then the money is more and more unbalanced. Actually, I mean, so that's I didn't make a real research study out of this, but I heard also from many sources that in Germany also the rich people accumulate more and more money. So I would have expected also in Germany to see this increasing. But okay, that's just one data source. Like if you really want to know this more detail, you can know how to calculate Gini yourself and try to see what data source you have. Still, I'm a bit astonished that also for Germany we don't see here a strong trend. Also interesting, for example, is the Gini curve in a country like China. For example, in China, so we had something which is also increasing in the range of 40–50%. That's maybe China. So question, of course, what does US doing? US was more unequal than, for example, Germany. US, we have something like this, and then we have also in the US a continuous increase in the Gini coefficient. We know in the range like in China. So that's USA. But then there are countries which are incredible with their Gini coefficient. For example, Brazil is one of the countries with the most unequal distribution, and here we are in there. Something like this. So here we have Brazil. But I mean, I don't want to make here an economy lecture. I just want to show you that these measures that we develop in this course here are very important measures in order to see how economies change in the future. So what's the tendency of the economics? And I mean, if you have an increase in a Gini coefficient of 10%, this actually means a lot, because this means in such a diagram here that this curve is 10% shifted to the side, and that means a lot of more money is suddenly accumulated by the more rich people. And I mean, this Gini coefficient then expresses all, now if I want to interpret it, all the unfairness in the distribution of wealth. Yeah? And so that's a very important thing to tell you about the unfairness of the system. And so it doesn't mean the absolute money is sometimes not so important, but the inequality of the distribution. Yeah? Of course, if we now take it more neutral and say, okay, we have a general power law distribution of whatever, of your email contacts and so on and so forth. And then you can also see, like in phone calls, for example, how did the Gini index increase over time. And so that's a typical sign we see with globalization or in social media. The more and more people get connected in the global world, we get more and more to the range of large Gini coefficients, where more and more is accumulated by the most popular choices. Yeah? So that was the measure of inequality. And maybe as a side remark, I don't want to show this to you, to derive this, but I still want to tell you another interpretation of the Gini coefficient. So we can measure the Gini coefficient as 1 over 2 times the expected wealth in the distribution, and now we have to integrate 2 times our distribution, and we weight this by the typical wealth difference between two persons, and we integrate this over dx and we integrate over dy. So the Gini coefficient is a kind of normalized difference of state variables or random variables in the distribution. Yeah? So again, it tells you how much the distribution of the wealth in this example differs in the population. Yeah? As an exercise, you can try to derive this yourself if you want, but I don't want to go too much into this. But so here, so we have seen if we have a power law distribution, yeah, and by such a plot, it's hard to characterize the distribution really good, because like half of the density under the plot is just close by the zeros, by the smallest value, by the cutoff. But to the right, the tail of the distribution is so large, it goes and goes and goes and goes to the side that we cannot really see it. Yeah? And so that's why I think this discussion of this Gini and inequality measures is so important, to see really how much is really accumulated in the tail of the distribution. So much for this discussion of power law distributions, and yeah, so we will continue this in the next videos. Thank you for the moment.